systematic treatment of equilibrium. I think this is really, activity is getting into more real life stuff. But I never really liked activity because you're introducing fudge factors, it seems to me, just to get the answer in real life, which I guess is what you got to do. But so I like this better because it really illustrates much more real life, real world situations and problems. And you'll see, we'll show some down here below. But what it really comes down to is, complex equilibria where you have more than one thing going on at once. Notice how there's not just one reactant, one product. I mean, there's multiple equilibria going on at the same time, and they're all simultaneously valid. So what it comes down to, it seems to my mind, is a 5-step process to figure these systems out. So what's an example of these systems that I'm saying that are so complicated? Well, let's start with the top one. What is the pH of point, how many zeros is that? 2, 4, 6, 2 times 10 to the negative 7. What is the pH of 2 times 10 to the negative 7 molar HCl? Well, is HCl a strong acid? Yeah. And I mean, it doesn't even look like activities would you even care because there's hardly any ionic strength here at all. And you'd think you could just take negative log of 2 times 10 to the negative 7, and you'd be done. But you're not. Because does water fall apart, dissociate on itself? Yeah, right? But to a very small degree, right? Like this small degree. That's the problem. Because Kw, what is Kw? Kw is 10 to the negative 14. That has to equal hydrogen ion times hydroxide. Well, hydrogen ion alone from water dissociating naturally at 25 degrees Celsius is 10 to the negative 7. You've got a contribution. You're off. You could be off by as much as 100%. So, and it's important. So you can't just take the negative log of this. It's going to be much more complicated. Okay? What is the pH of 0.085 molar phosphoric acid? Okay, now I told you what was complicated about this one. What's so complicated about the next one, the one in purple? Oh, there's 3 forms of phosphoric acid, right? We're interested in pH, but that hydrogen ion is tied up in this form, H3PO4. It's tied up in what other form? H2PO4. H3PO4. H2PO4 with a minus. HPO4 with a minus 2, right? And there's phosphate, but that's not tying up any hydrogen. So then you could write a Ka expression for each one of these. You can look them up, Ka1, Ka2, Ka3. Write them all out. All these equilibria are going on at the same time. Hydrogen ion is spread out and distributed over all these different forms. So you can't just, it's not a straight Ka problem. What is the concentration of carbonate containing calcium carbonate solid, 0.34 molar carbonic acid, and 0.013 molar HCl? What makes this a complicated question? There's a lot of stuff going on there. Shelby, what do you see that makes this complicated? I want to know the concentration of carbonate. If it was just for, if I could get rid of everything else and just talk about the solid, you'd say it's what type of problem? Anyone here? KSP, right? If I could just worry about just the solid. So I've got a KSP equilibrium going on. And then I've got this stuff. It doesn't look like it's tying up carbonate, but it is. What forms of carbonate are being tied up here with this weak acid? Ooh, yeah, HCO. I hear HCO3 minus. What other form of carbonate? CO3 minus 2. That's coming from there. There's one more. Why do we say H2CO3? Because some of it doesn't dissociate. It's a weak acid, so you have to name it. It exists. It exists. these weak acids are almost like precipitates. Man, they just form. They want to form, and a lot of it. Look at all those different forms carbonic acid is in. And then you've got some HCl in there to kind of mess things up too. So there's multiple equilibria going on at the same time, simultaneously. So how do we handle that stuff? That's the big goal. And I think we'll handle that by the end of this. I think we call this day 22 and day 23. By the end of day 23, we'll have all this figured out, I think, with our 5-step program. Okay. So let's start with a little review. The general equilibrium constant expressions for Kw. We said Kw equaled what times what? Do you remember? Where's Christina? Where'd she go? Oh, is it Javier? Kw is. Oh yeah, K times. That's one. Yeah, but that's not the one I was shooting for. The Kw is the I. Yeah, that's not the one I'm shooting for. Here you go. There's only one more left, I think. Kw is. We have that one. 1 times 10 to the negative 14. Hydrogen ion concentration times hydroxide. That's the one I'm after. This is the one I'm after. I mean, they're all valid, except I'm after this one because we're going to be writing a lot. Whenever we have hydrogen ion or hydroxide involved in our chemical system, we have to write this. Okay? That's why I'm writing it. Ka. Destiny, what was the general way that we wrote the Ka expression? Right? I think we called our weak acid, didn't we just call it HA or something like that? And then, so then Ka would be what over what? H plus, yeah.
And then
A minus, good. Good. Okay. So being able to slap these down quick will make your life a little bit easier. That's how we write our Ka expression. Our Ksp expression. Oh, Marlena, how did we write Ksp expressions? Yeah, they're always equal to some number. You look it up in the book. Just like the Ka, they always equal some number. So did Kw. But Ksp was, how do we write our Ks? What will they end up looking like? These expressions. What over what? Do you remember? Concentration of the, you have products over reactants, and the products are always, it's Ksp, always ions. That's what I kind of picture in my head, is the concentrations of all the ions all over one, the solid. Okay. And you have to raise the ions to their right stoichiometric coefficient, the right power. Okay. So just a little review. Writing charge balance equations for chemical systems. Charge balance. Well, if you grab, I don't care what liquid or what solution, you never get zapped by it, right? So the entire charge, well, I should read the sentence, I guess. Charge balance equations can be written for a solution that contains charged particles because the overall charge of the solution is neutral or same thing, 0, right? I like saying 0 because you think neutral, and well, what number is that? 0 is just easier to remember. Okay. So here is a solution. It has all these ions in it. And we need to write a charge balance equation. So all they're saying is, right, the concentration of all the positive charges, right, has to cancel out the concentration of all the negative charges. But realize some stuff is much more charged than others, like phosphate. 3 times more charged than chloride. So you need to take the concentration of phosphate into account by a factor of 3. Okay, so pretty much all we're going to end up doing is taking the charge and putting it out front times the concentration. So, and putting all the cations on one side and all the anions on the other. So before we do that, though, I just want to identify. This is going to be one of the. This will be one of the last steps in our 5-step program. We'll identify all the ions. And you list them out all nice like this, and then it's a lot easier to write the charge balance equation. We'll write the cations all on one side, and the anions all on the other. Well, that's my only cation. Phosphate. And hydrogen phosphate. And oh, does this have a charge? Nope. So he doesn't go in there, right? And dihydrogen phosphate. Okay. And whatever the charge is, multiply it by it. Well, so I guess you'd have 1 times sodium is all. All right. Chloride again is 1. Oh, there's a phosphate. That's 3 though. 2 and a 1. Okay. So that's our charge balance equation. It has to hold true just because we know solutions that have a total charge of 0. Okay. Make sense so far? We kind of jumped ahead a little bit, but it's just covering a concept. Here's another concept. Writing mass balance equations for chemical systems. So we've wrote charge balance. The solution has to be neutral. Mass balance. Mass balance equations take into account the fact that when the concentration of a salt is known, and you pretty much always know the concentration of a salt. Look at these guys, right? When the concentration of a salt is known, the concentration of the cation in all its forms in the solution is equal to the concentration of the anion in all its forms in the solution. So I know it sounds weird to say this, but it really helps me to figure these out. The cation in all its forms, anion in all its forms. And a lot of the times, it's not even going to fit. For example, let's take a look at this first one. The cation is what for A? Sodium. And the anion is chloride. And sodium doesn't have any other forms, though, right? I mean, sodium isn't all. What form is it a conjugate of an acid or a base? No, it's just sodium ion. It's not a conjugate acid or a conjugate base. So that's really pretty much the only question you can really ask yourself. So sodium in all its forms, all you have is sodium. Now, is there a 2 or anything down here? What number is down there? It's a 1, right? So the concentration of sodium in all its forms has to be 0.001 molar. So it's a lot of English to explain to write just this. But it will help when we get into things more complicated. The concentration of sodium in all its forms has to be 0.001 molar. The concentration of chloride in all of its forms has to be 0.001 molar. Now, chloride is a conjugate base, but it's a conjugate base of HCl. Can HCl exist in solution to suck up some forms of chloride? It's a strong acid. You can't form a strong acid. So chloride in all its forms is just Cl minus. So the concentration of chloride in all its forms, 0.001 molar. So 0.001 molar has to equal the concentration of chloride in all its forms. And you wouldn't write HCl because that doesn't exist. Right? You can't form a strong acid.
It's because
Yeah, you can't form a strong acid. Okay. B. The concentration of sodium in all its forms. There's only one form of sodium, but still, I still like to say it. The concentration of sodium in all its forms, because I don't screw up then, has to equal what number in this case? 0.002. Because look at the formula. Good. You caught it. Okay. Okay. The concentration of sulfate in all its forms has to equal what number? 0.001? Right? Right? Sulfate. So sulfate, don't worry about the forms of sulfate right now. Just all the forms of sulfate have to be 0.001 molar, right? Because look at the chemical formula. It's a 1-to-1 ratio. So 0.001 molar have to equal the concentration of sulfate in all of its forms. Okay. So what are the different forms of sulfate in water? This is always in water. What can you... SO4 minus 2 definitely is one of them, right? Are there any others? HSO4. And H2SO4. Something wrong? Don't forget your 6. Don't forget the 6. Yeah, you can't form strong acids. So don't go that far. But you got the right thinking, right? You keep going until you get the neutral compound, as long as it's not a strong acid. Otherwise, that's the game you play. Okay? Good. So 0.001 molar has to equal the concentration of sulfate plus the concentration of hydrogen sulfate. Okay.
So to get all the forms, you could say that you just keep adding H's.
Pretty much that's because the only game we're playing is with our review conjugate acids and conjugate bases. We could, the homework might get into complex ions, but I don't think so. I think it's just going to stick to acid-base systems. They're complex enough, you'll see. Okay. All right. Good question. So we'll start on this handout now. And using a systematic treatment of equilibrium approach, determine the concentration of each pertinent species in solution. So we need to identify all the species in solution, and then in the end determine all their concentrations. Okay. But we're not determining all their concentrations of everything is step 5. All we're doing, if you see this, all we're doing today is setting things up. We're setting the math up, setting up the plug and chug. We're going to set up all of our equations. If you have, let's see, the big picture is there's 4 ions. After you count up all this different possibilities, there's 4 ions total. How many equations do we have to get? How many equations would we have to set up if we have 4 different ions? 4. You see how the game is being played. So, mass balance, charge balance. All right, we're just going to be playing that game. But let's just start with so we're right here. Perform steps 1 and 2 for each solution or compound placed in water below. And then we'll perform step 3 and verify it can be solved with step 4. So we're going to stop right here. For today. Okay. Identify all pertinent species in the solution is step 1. So, Monica, what do I have present? I mean, you could actually say strontium nitrate too, but you almost have to know the solubility rules. I'm kind of skipping ahead a little bit. Can you ever form a solid with nitrates? No. I harped a lot on this group 1, how you can never form a solid with them. And I haven't really harped enough on nitrate, and there's one other ion that you'd never, ever form a precipitate with. It's actually a cation. Starts with an A-M, ammonium. So you'll never... So I guess that's what helps. By knowing these little tidbits of information, it helps me with these questions a lot. Because right when I see strontium nitrate, strontium 2 nitrate, I don't see solid at all. All I see is ions. And my brain just instantly breaks those up into ions. Why? Because I see a nitrate. Sodium fluoride. Again, ions, because I see sodium, right? So the book kind of expects you to be able to do that too. When you see a compound, you exactly know whether if it breaks up into ions. Okay. So what ions do we have there? What was I picking up? Monica. It's SR, but with what charge? +2, right? Cation's always first, anion's always second. SR +2. Another one. Eric, do you have any other ions present?
HSR? Oh, no, it'd be SR. So H minus.
Well, no. Well, strontium, think of it this way. With all of these, those Ka tables, right? You can't really add an H. He's not a conjugate base.
Right, yeah.
So you're done. You're done with strontium. You really are done.
You can't add OH minus to cancel out that charge. It's not the same way.
Oh, okay. If you're talking about, if you add OH minus, you're talking about strontium hydroxide. And if you add strontium hydroxide, we can go down that route. All we're doing is we're just pretty much introducing another variable. You have to introduce another equation that's KSP. So we're sticking with just Ka, Kb. What do they call those? Conjugates. We're sticking with just conjugates. So strontium 2 doesn't have any conjugate acid or bases, so you quit there. So the other ion would be, Marlena, what would be the other ion?
Just SR plus, right?
Just, yeah, Sr +2, because you have the 2 down here.
Oh,
Right, it has to be strontium 2. And what's the charge on, what's the other ion? NO3. Do you remember how this works? You guys remember how this works? What's the charge on the nitrate? -1. Now, if you didn't remember, had no clue, and these are, all of a sudden now they're important, because now you have to do charge balance. What if you totally forgot that nitrate has a negative? Now, you know it's negative, because it's the second one. But what's its charge? What is the number? 1, 2, 3. Where do you look to find that out? The bottom of the strontium, exactly. That's why I knew that this was strontium 2, because the 2 is over here. Right? So strontium +2, nitrate -1. Okay. Any other ions, Matt, or any other compounds? It doesn't have to be an ion. Like, so any other species present, right? Okay. So, see, we could, let me just try to confuse things here. Say SR NO3 2. We don't write him because of the what compound? What analyte? What anion? NO3. He's not going to exist, right? The solubility rule. So you don't write him. Go back to where I think what it was confusing Eric. He's adding in the H+, right? Trying to do this conjugate stuff. So you can't add an H+ to a strontium 2. Like, can I? No. But here's a conjugate base. You can always, anything negative can add an H+ to it. But does it make sense to write HNO3? Strong acid. So that's another one where you would not write. Okay. We know that it's water. So we could write H2O liquid. We could write H. If you have water liquid, you have H+, you have an OH minus. But there's no sense in, if we introduce them, we're just going to introduce another equation. So you can make these simultaneous equations as long as you want, but by just introducing more variables, then you come up with another equation. So what I'm trying to do is trying to stop. If I don't see, I only write an ion when I need it, right? And we'll get there when you'll see what I mean when I say you need it. We don't need it. We're done with strontium +2, and this nitrate can't form. It's such a weak conjugate base. It's never going to do anything in solution. So
it's like you couldn't have it for two reasons. One, because nitrate's present. Two, because it's a strong acid.
yeah, I guess true. Right? So nitrate is such a weak conjugate base, it's not going to do anything. There's no acidic or basic properties to it. You quit. Okay. So there's no reason to go on and write H+, OH minus. You can, but that is going to introduce more issues later on. So I'd say if you don't need it, don't write it. Okay. Okay. So write any. So that was step 1. Write any KW, KA, or KSP expressions for the involved species. So everything that we've done up to this point, you take a look at this. Can I write a KW? No, because using the involved species, we didn't write H plus or OH minus. If you did, then you'd write the KW. So that's why I'm saying don't make your life more complicated if you don't need to. We didn't write H plus or OH minus, so we don't write KW. Can we write a KA? Does the KA exist for this? No. No, there's no KA you can write. Can you write a KSP?
Not because we didn't include that, sorry. Right?
Well, you know what the problem is? Yeah, because
Oh, you have
Is
your
there a
ions.
KSP?
Well, you have your ions right there, right?
KSP means you have to be able to form a solid. There's something insoluble there, something that'll precipitate, according to those solubility rules. And nitrates, they're not going to do anything. There's no solubility problem to write. Where you'll see solubility is something like this. See where they see solid and saturated solution? So there's no trick questions in that sense. So there's no KW because we didn't write H plus or an OH minus. There's no Ka because no Ka exists for HNO3. KSP, there's nothing there that'll form an insoluble salt. So we just move on. So we move on. So we're done. There's nothing to do. We can't do anything. Because our pertinent species, using the language I've used here, it doesn't involve it. So we just move on. Write any charge or mass balance equations. So charge balance. How would you write the charge balance equation? Cations on the left, anions on the right. Okay. And then do what? 2 times this one. Good. Okay, there's our charge balance. Our mass balance. Mass balance. Okay. The concentration, again, I have to word it this way, I'm sorry. The concentration of strontium in all its forms, concentration of SR in all its forms, has to equal what number? Has to equal the 2.8. Good. Okay, now looking at our list here, the strontium in all its forms is just SR plus 2, right? So SR plus 2, strontium 2 is 2.8 molar. Okay. The concentration of nitrate in all its forms has to equal, everybody? It's 5.6 because there's 2 of them, right? It has to equal 5.6. So the concentration of nitrate, that's the only form there is of nitrate is this one. It has to equal 5.6. Okay. So this first question, you end up with strontium is 2.8 molar, nitrate's 5.6 molar. Well, we could have done that a long time ago without all this work. But the point is life is not going to be this easy, and it never will be, right? This isn't even a systematic treatment. There's nothing going on here, okay? But it illustrates the steps that we need to use when we do have an issue, okay? So verify number of unknowns is equal to number of equations. Yeah, I mean, we're plenty good, right? We have 2 unknowns, 2 equations, we're good. Okay, this question. Start with step 1. Start with step 1. Identify all the species that are there. And then once you identify all the species that are there, go on to step 2. Write any KW, KA, or KSP expressions.
So this would be permanent species. Would you put PbCl2 in there since you could do a KSP for that?
Well, PbCl2 is a solid. So he's already solved for. Their concentrations never. So the solids, just like pure liquids, they're not an unknown, right? They never show up in any Ka or Kw or any KSP expression. So they're not pertinent. They never change.
Oh, right, because the solid would be the one.
Yeah, so, yeah. Their activity is really 1, so they.
So then once you have like the plus 2, you do another
All right. So in step 1, you got Pb plus 2 and Cl minus. Okay, that's step 1. Was there anything to write for step 2? Yeah, definitely you can't write a Ka expression. Good. But you can write what expression? KSP. So you look up the KSP, whatever it is, for lead 2 chloride. All right? Products over reactants. Go ahead and write it in. Okay. Write any charge or mass balance equations. So right now we have how many unknowns? 2 unknowns. We have 1 equation. So we got to keep going, right? Write any charge or mass balance equations. Yeah, put chloride on one side, cations one side, anions on the other. Yeah, good. 2 leads and 1 chloride. Okay. Okay. So the mass balance is the same thing. Mass balance is harder to write. For me, mass balance is harder to write when there isn't a little molarity there. The concentration, when there is no molarity, I have to read it. Do you remember reading equations? What did you say when you see the equal sign? Like the concentration of chloride is the same as, or is, the concentration of chloride is twice that of lead. That's right. Concentration of chloride should be twice that of lead because there's 2 Cl's. See how it's harder to see when there's no molarity there? Well, it doesn't matter because we're done anyway. You could just not even worry about mass balance because you have 1, 2 equations, 2 unknowns, you're done. So we don't really need to worry about it anyway, even though they're the same thing. Okay, try C. So if you're not sure what all to write in step 1, just go on. Because you can always add things to that if you find out that you need them. See what I mean? So if you see sodium and fluoride, fine. There might be more. Let's try step 2. Write any KW, KA, or KSP. You can definitely write what? KA, right? So step 2, write that KA. Products over reactants, right? H plus, F minus, all over HF. Whoops. We have to add 2 more ions up on our list, right? No, fluoride, remember? That's the one where I use it to memorize half the strong acids. You just got to remember HF isn't one of them, right? But HCl, HBr, and HIR. Okay, so do you catch this so far? So I have to add H plus, and I have to add HF up there, HF. Okay, that's just fine. You can add them as you go. I can't write a KSP. Can I write a KW using the involved species? KW was, we always said KW was H and OH equals 1 times 10 to the negative 14. We have H. So you have to write KW now. Right? So we have to write KW now. Simply because we have an H plus. But now I need to add what to my list? OH. Can I add Na? Someone said this. Can I add NaOH to my list? Strong base, and it's Na. Right? It's never going to form. It's never going to go with anything. It's always forming aqueous solutions, 100%. So you're never going to do that, right? So can we write any other KS? Can you write any KSP? No. And since we wrote the Ka, it's not going to help anything to write the Kb. You're going to end up with one of those equations, 1 equals 1. So you've already used up the information. So I always write KAs and that's it. That's why it's in the list, all it says is KW, KA, or KSP. KB is not even listed.
So like a KW, you can write anytime you see H plus.
Yeah, exactly. If you see an H plus or an OH minus in your list, you have to write KW.
KA you do when you see a conjugate base.
Yep, or a weak acid.
And then a KSP you do when you see 2 things that could form a solid.
Well, here, yeah. It has to be an insoluble solid.
But we didn't write a K. Oh, we did write a KSP for that.
Yeah. Okay, now we need to write charge balance. So go ahead and write the charge balance. Everything we ended up listing, exactly. All the cations on one side, anions on the other. And don't write HF because it has no charge. Mass balance. Okay. Okay, last one, then I'll let you go. Mass balance. The concentration. I'm going to make space just so you can see this here. The concentration of sodium in all its forms, has to equal 2.1. And there's no other form for sodium than this, right? So we're done with sodium. The concentration of, what's the other ion here? F. In all its forms has to equal, everybody, 2.1. Okay, so go back up to the list. The F's in all their forms, there's two of them. There you go, F and HF. All right, now hopefully we have 1, 2, 3, 4, 5 unknowns. Let's see, here's one equation, 2 equations, 3 equations, 4 equations, 5 equations. It's solvable, okay? May not be fun, but it's solvable. So I think your homework is to finish this sheet, and maybe there's some, I don't know, some homework or something in the list. I'm not sure. Okay. So come by. I'll be glad to work on this stuff with you. Oh, your exams.